Hi everyone, we are coming back to lesson 7.4 to finish it up, and so this is a continuation of our 7.4 logarithmic properties, and we're focusing on something called change of base formula. Now I have required several of the properties of logarithms to be memorized because it's really important to use when you're working with them. So we have those videos out there. We also have some review videos for you to look at. So we have several properties, like I said, that need to be memorized in order to work. However, this is one of the formulas that I don't like to say memorize. I would rather do the math and the algebra to find this. But if you're into wanting to memorize this formula, that is okay. It's a great shortcut, but by doing the math, we are doing several things. We're practicing our other properties, so we're less likely to forget them. We also have a sense of idea of how this works rather than what goes on top and what goes on bottom. So I want to show you the way I think it should be done. But if you're looking at this shortcut, you have to make some sense of it, and by me showing you the way to do the math on it, it will make more sense. So I have log base b of x, and this would be something like log base 4 of 8. And so if I convert my problem, log base 4 of 8, into exponential form, I have 4 to some power equals 8. And so if I'm thinking about it, 4 to the first is 4, and 4 to the second, 16. So I know that the power x has to be between 1 and 2. I just would have to figure out what it is. And I could do a little guess and check and use my calculator to help me play with those numbers. But to make it more accurate, we can use this change of base formula or use the math behind it, which I'm going to show in a couple minutes here. So the formula basically tells you to change your base to anything you want. Now, if I had a choice of changing my base, I would change it to base 10 because base 10 is what I can use in my calculator. The way I would memorize this, if I was really just trying to memorize it, it's log base b of x. Your base is on the bottom, so there it is, and the log of what you're taking the log of is on the top. So bottom base goes down on the bottom of your fraction, and what you're taking the log of goes on top. And again, the base has to change to whatever you want, and they have to be the same. So you might do a base 10 and a base 10. And so that will always work for you. What they have here is they change it to base 2. And the reason they did that is if I come off to the side and I look at this, 2 to the x equals 8. Well, x is 3 for the first part. And in the denominator, they have 2 to the x is 4. And x would be 2. So my outcome would be 3/2. So log base 4 of 8 is 3/2, and I found that by changing to base of 2. Again, most of us would just change to base 10. There are rules just like before. A is a base, and in here, and B is a base that we started with, and so your base has to be greater than 0, but it can never equal 1. And that's because you can't have a base of 0, and if your base is 1, anything 1 to any power is always going to be 1, so it breaks some of the rules. Okay, so let's talk about what we started with. This would take us back to the very beginning when we talked about using logs to solve for unknown powers. So that's the big rule that I want to remind you of. Logs, they solve for unknown powers, which is a really big deal. So how do I know to use a log? Well, I have log base 4 of 8, and that log is not helping me. All right, in log form, that doesn't help me. I can't put it in the calculator. The first thing we did was absolutely, I could just jump to my shortcut, but I'm not going to. The first thing we did when we had a log was we set it equal to something, so we had the 3 components, and we took it out of log form and changed it to exponential form, which is one of those basic concepts that you really need to know for any of this. And so I'm going to take this out, and it's going to be 4 to some power equals 8. Okay, so log base 4 is my base, 4 to the power of x is 8, log solve for exponents, that's why x is my exponent. And now that I have 4 to the x equals 8, I can again think about what am I doing. It's the same problem we started with up here. I can ask myself, what am I doing, what's the power of x, and I know it has to be between 1 and 2. One of the properties that we will be talking about later, but I'm going to jump into it now, is just taking the log of each side. Just like anything else, if I multiply both sides by 5, I multiply the other, do the other side. If I take the square root, I would take the square root. So I too can take the log of each side, and I'm choosing to take log base 10 of each side. So what I have here is I'm going to clean it up. Log base 10 of 4 to the x equals log base 10 of 8. And so by taking the log of each side, I can go ahead and use my product property. So I want to remind you of this product property. It was in prior notes. And so anytime I have a log base b of a to the power of p, anytime I have a log to a power, has to be a log to a power, the power can come out front. And it's called a power property of logarithms, and we use the product then, p times log base b of a. So I'm using several things here. First, I'm changing it from logarithmic form to exponential, so that's good practice. Second, I'm using my power property of logarithms. So this is going to come out and create multiplication. So it's x times log 4 equals log 8. And now I'm really just using some simple algebra skills here. I have x times log 4. And I need you to remember that log 4 is a number, okay? If I type in log 4 in my calculator, close those parentheses every time, you see that I get this decimal 0.60205 and several nines. So we could round it to 0.602, 0.6, but I'm rounding it, okay? So I have lost some of the accuracy here. So I would like to leave log 4 as its number, okay? But log 4 is one number. You can't separate the log or the 4. And again, we can get this decimal, but I prefer to leave log 4. It's the same as using your pi key, where pi is going to give you a more accurate answer compared to rounding pi to 3.14. So I'm choosing to leave this, but it's x times this number. And so I get rid of multiplication by simply dividing it, and that's going to cancel it out. And if I divide this side by log 4, I divide this side by log 4. And that's it. It's as simple as that. And you can see, now they had log base 2 of 8. We have log base 10 of 8. But we have, our bases are the same and our numbers are the same. So I want to clean up a couple of misconceptions and issues while we do this first problem. I have log 8 divided by log 4. And again, I'm always going to choose base 10 because I can use my calculator. Some of the issues that we have in doing this is getting to the end and making simple mistakes. One of the mistakes people want to do is they want to cancel out the logs. They used to say, well, it's division, so they should cancel. They want to cancel the logs, they want to reduce the numbers. You can't do that. You can't look at this and say it's the log of 2. So I bring that up because I wanted to remind you of our properties. We had started with talking about these properties before, that when I have multiplication, it leads to addition. But notice this is a single log broken up into 2 individual logs. And I bring that up because it goes directly with our division. And this is what I wanted to remind you of. I have a single log here of 16 divided by 2. So this is equivalent to log base 5 of 8 because I have a single log. And that single log brings us to subtracting individual logs, same base. Okay, very different. Single log with division leads you to subtraction. But these are not single logs. This is log 8 divided by log 4. That's why these don't cancel. Log 8 is a number, log 4 is a number. So when I go to type this in the calculator, there's nothing reducing or simplifying here. I'm going to type in log 8, and it's really important to close those parentheses, and I'm going to divide it by log 4. And I'm going to close that parenthesis for good measure. And I get 1.5, or 3/2. So we do get that x is 1.5. We should be able to convert that to 3/2, but just in case, your second function, fraction to decimal, would turn that into a mixed number. And then I can take my second function and I have my mixed number to improper and hit enter, and there is my 3/2. So 1.5, 1.5, or 3/2. And that is what we get. Now, let me show you the incorrect way to put this in. If I type in log 8 and I do not close parentheses, and then I divide by log 4, whether I close these parentheses at the end or not, it doesn't matter, I get a very different number. I get 1.12. And what your calculator is doing is it's taking 8 divided by log 4 and then taking the log of that outcome. Okay? So you have to ensure that you have closed these parentheses. The end one, not a big deal, but I would still close it, and we get the proper answer. So how do I know if I'm right or wrong? I'm actually going to go back to the beginning where I had taken my log form and change it to exponential. 4 to the x equals 8. I'm just going to type in 4 to the 1.5. And there it is. I get out 8. If I type it in to that last incorrect answer, which was like 1.12, and I type in 4 to the power of that answer without even rounding it, I get something really wrong. That is not 8. So it's good to double check yourself also. All right. Last idea I want to talk about, same thing. This would be you have base 10 to some power. And so we could take this off to the side and we could figure it out, but it'd be a little bit messier. Up here, we could take this off to the side, log base 2 of 8, because we could use mental math. But if I have this, it's a base of 10 to some power equals 8, I'm going to get a decimal, okay? And so that's log 8. That is 0.903. So if I take 10 to the power of 0.903, I'll get really close to 8. And so that's why this one I can't really do the mental math off to the side, because I have log base 10, where up here they worked it out to use mental math. Okay, so we're going to stick with log base 10 and use our calculator. So let's continue some examples. I know this was a long one, but I really want to talk about all those important features. So again, same deal, log base 9 of 27 is not helping me. So I'm going to go ahead and set it equal to a variable. I just choose x, maybe you choose n, and I'm going to change it to exponential form. 9 to the x equals 27. Okay, so then I'm going to come in and say, hey, I have an unknown power. Like, that's what I'm looking for. Logs are equal to exponents. Change it to exponential form. 9 to some power is 27. So I am coming back to that key idea. Why am I using a log? Because logs solve for unknown powers. And by coming in and taking the log base 10 of each side, I am really doing the long version instead of jumping to the shortcut. I can take the log of each side. Now I can use my power property where that comes out front, and I get x times log 9 is equal to log 27. Now if I come back to what I wrote here in red, 9 to the x equals 27, 9 to the first is 9, and 9 to the second is 81. So I know it's between 1 and 2. Might be 1.5 again, might be such, not a pretty number. So let's see what it happens to be. And now that I have x times log 9, I'm going to divide both sides by log 9. So that can cancel and divide by log 9. And so this is really where we're using our calculator. I'm not able to do base 10 to some power gives me 27, other than guessing. So we're going to use the calculator since we made it log base 10. And I apologize for the glare. So it is log 27 divided by log 9. Make sure you're closing your parentheses. And we do get 1.5 again, which is just a coincidence from our last problem. So x is 1.5 or 3/2. Okay, so we figured out what log base 9 of 27 is. All right, so we have another one here, and it's log base 8 of 16. And so I'm going to take it out of exponential form. So set it equal to x, and that would be 8 to some power equals 16. Okay, so real important we have that base. I'm again going to come in. I didn't really leave room for this, but I'm going to take the log of each side. And now that I took the log, I'm going to bring that out for multiplication. And so I have x times log 8 equals log 16. And now I'm going to come in and divide both sides by log 8, divide by log 8, and that's going to cancel out. Again, we're going to put this into our calculator just as is. So log 16, close those parentheses, divided by log 8, close those parentheses, and we get 1.3 repeating. Okay, so I'm going to write that down. X is 1.3 repeating, and that is my answer. How do I check it again? I'm going to come back. I'm going to take 8. Now if I go to the power of my answer, I'm using that option where I hit second and my answer key there, I'm going to get 16 because my calculator hasn't rounded it, it held that answer. If I put in 8 to the power of 1.3, I get really close to 16, but not that close. Okay, 1.3 is actually a pretty far stretch from 1.3 repeating, so I only get to 14.9 instead of 16. If I come in and add a couple 3s, this is why accuracy is so important. let me do this again. Let me add a couple 3s. Now I'm really close. That made a difference, okay? I only added in 33 thousandths, wait, tenths, hundredth, thousandths. I only added that in, and it made a difference. So if I came in and deleted one of these, you can see I'm at 15.88. But again, if I only did 1.3, what's a difference? 14.92. So I think I'm wrong. But again, if I come in and throw in a couple 3s, look how close to 16 I am, okay? So just wanted to bring that up. All right, I wanted to do a couple more extra examples to add on to here. So let's go ahead and do a little bit more. I have, for example, one to solve that's a little bit different. So I wanted to bring this up. And it would be, we'll call it example 4 here. And it is that I have a log base 8 of 12 to the power of 3. And that's different because now I have that power of 3 there. Now here's the deal. If I take in my calculator 12 to the 3rd, I can do that. So I could simply rewrite this problem as log base 8 of 1728. And that's not horrible. But if it was something like 12 to the 4th, or 12 to the, I don't know, 8th, I don't want to write that number down, okay? So one of the things we can do is, yes, we can apply that and we can use this and just go through the same motions we were. But if I have this power here, what I'm going to do, because I want to show this, is I'm going to bring this 3 out front. And we've done this before. It's 3 times log base 8 of 12. And so I'm going to leave that 3 there, and I'm going to find out what log base 8 of 12 is, and then I'm going to come back and finish the problem. So that's all I'm doing. I'm leaving the 3 out front. I brought out front using my power product, and I'm going to go ahead and work this math and do 3 times that outcome. So something we've already practiced. The reason I really think it's important to show is because this number, 12 to the 3rd, is reasonable. It's manageable. But there are some that are not going to be manageable, so the best thing is to bring it out front. Okay, and we did this when we did our mental math. So off to the side, I'm going to work with just this part. So the reason I brought that 3 down is I don't want to lose that 3 and forget that I need to finish the problem. Okay, so let's just sort of leave that off to the side there. And I'm going to deal with this. So this would be 8 to some power equals 12. Okay, well, 8 to the 1st, 8. 8 to the 2nd, 64. So I know my numbers between 1 and 2. And because 12 is closer to 8 than it is 64, then my power must be closer to 1. I'm going to sneak in here and take the log of each side. And that brings that power out of its position. And I now have x times log 8 equals log 12. And then I'm going to divide both sides by log 8. Divide by log 8. Okay, so that is going to cancel, and I get x. I'm going to put approximately, and I'm going to type in my calculator, log 12 divided by log 8. Again, closing my parentheses, and I get 1.1949. Okay, now this number I am rounding, but it does end. It's not irrational. Keep as much, well, I'm just going to write it all out here. And now what I'm going to do is I'm going to use my calculator. I'm going to round here. It's 3 times that number, 1.195. But I'm going to go ahead and put it in my calculator using that. So 3 times my answer, and I get about 3.585. So that is my, I'm not going to say x equals, so I use x for the power, but that is my final answer there. Okay, so if I take my number that I rounded and I take 3 times 1.195, you can see I get the same rounding, so we're good. Okay, again, we could have solved it using this, but I wanted to show you how to bring that 3 out front. All right, let me show one more example of using some of our skills, and it's a word problem. So it's a nice application problem, and so I'll give you a minute to read through it. And this is one of those problems that really takes a lot of thought with our properties. Okay, so we are talking about the Richter scale to talk about energy or magnitude. So let me read through this. The Richter magnitude of an earthquake M is related to the energy released in ergs. Okay, we talk about ergs, it's a really large number. So they took something, a gentleman named Richter, took this and put it on a scale to make it something that we can discuss more easily, we can put in the news, we can record, and we can understand literally the magnitude of the earthquake without trying to figure out what this number represents. So we are talking about this, and you could take some time and research some of the earthquakes that have happened in history, some of the earthquakes that have happened more recently during your lifetime that you've heard on the news, just to get an idea of how severe they were, and what that means in erg. So the formula for the magnitude is 2/3 times the log of E, and E stands for the ergs that were released, the amount of energy released, so we don't know that number right now. And it's over 10 to the 11.8. So the 2/3 and the 10 to the 11.8 are a constant. That's part of the formula. But the magnitude depends on the amount of energy. Okay, so all we have to do is put in the amount of ergs we have here, and we can find out what the magnitude is. If we know the magnitude, we can work backwards and try to find out how many ergs it was. So in 1964, an earthquake centered at Prince William Sound in Alaska registered a magnitude 9.2 on the Richter scale, which is very high. Okay, so what we want to do is we want to find out how much energy was released. So normally we just plug in the answer and we use some algebra and we solve for the unknown variable. Or we could use inverse functions, find the inverse. But this is a little different because it's log. So we are going to just use algebra to solve for E, but we're going to use inverse operations. And this is where we really need to know our properties. So all we had to do was take the given formula, okay? We plugged in the magnitude and we want to find the amount of energy that was released, and that's measured in ergs. So plug that in, and the first thing I see is, oh my gosh, there's a log there, and we have an unknown in there. And that's really hard to solve for unless you know your logarithmic properties. We're going to start more basic than that. I want to peel this off. I mean, I'm really following my order of operations. I'm getting rid of any addition and subtraction first. And there is no subtraction here. So the next thing I'm going to do is look for any multiplication or division. So I am looking at this saying it's 2/3 times the log. And this is one number. I can't break this up. But since it's 2/3 times the log, I can get rid of it by dividing by 2/3. But I prefer not to divide. I'm going to multiply by the reciprocal of 3/2. And that is going to cancel with that. And over here, I'm going to multiply by 3/2. All right, so I'm going to use my calculator just to make sure. And I'm going to take 3/2 as a fraction, or you could use parentheses and do division there, or 1.5. And we're going to multiply that by 9.2. And we end up with 13.8. So I'm going to go ahead and use that 13.8 to simplify that. And that equals the log E divided by 10 to the 11.8. Okay, a couple of things that are really important here is to realize this is a log base 10. Okay, that's important. Second thing to remember is that, wait a minute, I have a single log and I have an unknown divided by 10 to the 11.8. And so I need to get this by itself. And I can't multiply out by 10 to the 11.8 because it's not just E divided by that, it's the log of it. So in order to break this up and get this denominator out of there, I'm going to go ahead and use my property where if I have division of a single log, I can break it up to subtraction. So I have 13.8 equals log, I'm going to write that in, base 10 of E, just as a reminder, minus log base 10 of 10 to the 11.8. So I'm putting in that log base 10. Okay, why was that so important? Well, another logarithmic property, I have this log base 10 of E, and there's not much I can do with that. However, I see this guy right here, and I know that my outcome is simply 11.8. And that's really easy for me to see, but I'm hoping you see it too. Log base 10 of 10 is 1. It's like log base B of B. Okay, so I'm using that property, log base B of B is 1, because B to any power, or sorry, B to 1 will always give me back my outcome of B. So I did that, and then I pulled my power property out front. And so I have 11.8 times 1, which gives me 11.8. Okay, so again, this is a lot easier to do when you know your properties. Now that I have that, I'm going to do some simple algebra again. I'm going to go ahead and get rid of this 11.8 and get rid of this 11.8. And I end up, oh no, I end up with 25.6. Let me change colors here. 25.6 is equal to log base 10 of e. Okay, now this is where sometimes people get stuck, and it's right here. It's something we've been doing the whole time. Okay, so we definitely were applying some properties that we might not have been sure of before. And now we're doing something we know. There's two ways of doing this. And the way that I think you would see it is, hey, I have log base 10, I can put it in my calculator. Oh no, I can't, because I can't take the log of an unknown in my calculator. So let's get this out of logarithmic form and make it 10 to the power 25.6 is equal to e. Guys, you just solved this problem. You know that the amount of ergs given off, the amount of energy, is 10 to the 25.6. That's it. You're done. 10 to the 25.6. Let's go ahead and throw that in the calculator. 10 to the 25.6. And wow, we get a really big number. I'm not sure if you can see that well, but it's 3.98, and there's a whole lot of decimals, times, if you can see that little times 10 to the 25th. So that is scientific notation. So the amount of ergs given off, E, is I'm rounding this, 3.98 times 10 to the 25th. What does that mean? Well, that means I'm going to take this decimal and I'm going to move it 25 units to the right. And for every spot, when I move this, I'm going to fill in zeros. Okay, so it is a very large number. That's why I'm writing my answer in scientific notation. So 3.98 times 10 to the 25 ergs. So that's it. We solved it. That's how much energy was released. But if they would announce this in the news, a lot of people wouldn't understand what that means. But by having the Richter scale, we now can compare earthquakes much easier with a more manageable number for us to compare one earthquake to another. All right, just as a side note, another way we could have solved this, we had that 25.6 equals log base 10 of e. I prefer just to knock it out of logarithmic form and put an exponential, and the answer fell right into our lap. The other way you could have done it is you could use one of the properties that we had done before, and that property is, take a second and show you real quick. That property is right here. B to the log base b of x is equal to x. So I had 10 to the log base 10 of 2, and that's equal to 2. So what I'm going to do is I'm going to come in on both sides and raise this to my power. So it's 10 to the 25.6 is equal to 10 to the log base 10 of e. 10 log 10 cancels out, and there it is again, guys. E is equal to 10 to the 25.6. So I could do it this way too. I just think more of us would take it from logarithmic form to exponential and find that answer. Okay, so that is it for change of base, which is really solving for unknown exponents using logarithms. And I thought this was an interesting problem, and maybe you'll take some time to look up some more information about earthquakes to compare.